The Australian Institute of Physics, the Teachers Guild of New South Wales, the Royal Society of New South Wales, and the Australian Chemical Institute acknowledges the traditional custodians of the country throughout Australia. We recognise their continuing connections to the traditional lands and waters and would like to pay the respects to their elders, past and present. Ladies and gentlemen, my name is Dr. Frederick Osman. As the President of the Teachers Guild of New South Wales and the Secretary of the New South Wales Australian Institute of Physics, I'd like to please to welcome you this evening to the Concord Golf Club for our Frontiers of Science Forum presented by the Australian Institute of Physics, the Teachers Guild of New South Wales, the Royal Society of New South Wales and the Royal Australian Chemical Institute. Tonight, we are very privileged to be joined by the Honourable Alistair Henskins, the New South Wales Minister for Science, Innovation, Technology, and the Minister for Skills and Training and the Leader of the House of the Legislative Assembly, along with Professor Johannes, Professor Benjamin Eggleton, Professor Chris Tisdell, and Professor Martina Stenzel, as the speakers at this year's combined Frontiers of Science Forum. I would also like to thank Ian Woolf from Diffusion Radio, who will be involved with our panel discussion later this evening, exploring the major discoveries and theories of physics, mathematics, biology, and chemistry. The format schedule of this evening will be our presenters to speak for 25 minutes each on their chosen Frontiers of Science topics, and this will conclude with a panel discussion and Q&A at the end. So please hold those questions to the panel discussion session after the talks. We are also videoing this event so we can make it available for everyone that could not attend tonight. Without further ado, I would now like to invite Dr. Susan Pond, the President of the Royal Society of New South Wales, to provide the welcome on behalf of the organising associations for the event. Thank you, Susan.
As Fred said, I'm here tonight with the privilege of representing the Royal Society of New South Wales as its president. Since it was founded now 201 years ago, the Society has been a nexus of ideas and discovery, challenging us and the people of New South Wales to think differently, exposing them to the latest research, and promoting awareness of some of the major issues of the day. It's a flourishing society, and I've already met several members and fellows here tonight, which is made up by more than 650 members from Greater Sydney and across New South Wales through our branches in the Hunter region, Western New South Wales and the Southern Highlands branch. The Society also flourishes by forging partnerships, such as the one tonight with the Australian Institute for Physics, the Teachers Guild of New South Wales and the Royal Australian Chemical Institute. Together, we're all driven by the idea that research, inquiry, discussion and debate are critical more than ever to our future. So I am looking forward to tonight's presentations and discussions in this Frontiers of Science Forum presented to you by 4 organisations. Welcome everyone and thank you, Fred.
Thank you, Susan. Now, on behalf of the Australian Institute of Physics, the Teachers Guild of New South Wales, the Royal Society of New South Wales and the Royal Australian Chemical Institute, I'd like to welcome the Honourable Alistair Henskins, the Minister for Science, Innovation, Technology and the Minister for Skills and Training, to open the 3rd Frontiers of Science Forum and to welcome everyone tonight. Thank you, Minister.
Well, thank you very much, Fred. And can I just say how wonderful it is to be here tonight to open this forum. I actually had another engagement tonight which I have to go to, so unfortunately I'm not able to stay, but I was very insistent with my office that I did want to come along and meet you and to say a few words tonight, because I believe that what you are doing is so important for science and innovation within our state and indeed our country, that I thought it was very important that I came here tonight to give you a few words and to thank you for the work that you do. We have so many world-leading scientists in this state and indeed in our country. And of course, none of them would be the scientists that they were without someone who had inspired them with regard to science during their lifetime. And so to be here tonight to acknowledge the important work of our science teachers and to be here with so many members of four ancient, and I don't say that in a pejorative way, but ancient organisations, the Royal Society of New South Wales, which, as Sue said, is 201 years old, the Teachers Guild of New South Wales, which is 135 years old, the Royal Australian Chemical Institute, which I think, if my maths is right, is 105 years old, and the Australian Institute of Physics, which is a baby at only 59 years old. These are ancient organisations, and they were established for a really important reason. And that is, as you all know, that science is at the very foundation of the world. It's so fundamental, it's so important to, as Susan said, be interested in why we are, why the world is the way that it is. And that's a continuing inquiry and investigation, which is very important not only to understanding who we are, but of course understanding what the future is going to look like. And that's why in my portfolio, I'm the first science minister in New South Wales, but I think it's so incredibly important that we have at this moment in time a focus on science and a focus on the possibilities. Economic rationalists will of course say that there are very important economic reasons for why we should be focused on science and innovation. We need to, as a society, really capitalise on our world-leading scientists because they will provide the avenue for the jobs of the future, for the world of the future, and for the future prosperity of our country. We've so long relied upon primary industry, whether it be mining or agriculture, for our national wealth. But really the future, I believe very strongly, is going to be the sort of industries and jobs which our innovation arriving out of our research and development will provide for our nation. So I must say I was very fortunate. My mother was a scientist. My grandfather, her father, was a doctor, a medical doctor. My father has an engineering family. I'm kind of almost a black sheep because I became a lawyer, I've been very fortunate, I think, to be in an environment where there's been a very heavy interest in science and mathematics. Maths was my favourite subject at school, I've got to confess. These are all the foundations, of course, of having a real interest in the way that the world is. So can I just say the New South Wales government has really been trying to push along research and development. We've had a number of policies. We've actually got a great chief scientist and engineer in New South Wales who has a unique experience as his area of interest. He's a professor at Sydney University in machinery and mechanical engineering, but he has also had a really interesting life in terms of working in industry as well as academia and so on. And so he has really been driving some great initiatives that have been occurring within our state. We have an acceleration research and development in New South Wales action plan, which sets out our recommendations on how R&D activity should occur in our state. We've been trying to do everything that we can to facilitate New South Wales getting federal government research grants. And now, as the Minister for Science, we hope to be doing so much more to facilitate scientific research in our state and particularly in our universities. I must say, collaboration between your 4 societies is really a great exemplar to what we are trying to achieve in science more broadly. The collaboration that's going on within universities for scientific research, the collaboration between universities that is going on, and then the broader collaboration between universities, industry and government, really I think is an exciting future for scientific research in our state. So can I wish you all the very best for this, your 3rd Frontiers of Science Forum. I deeply hope that I can stay for the next one, and I hope that there are very many more of them to come. Can I thank the teachers in particular, our great science teachers, for the way in which, whether you're a primary school teacher, a high school teacher, or a university teacher, thank you for inspiring our would-be scientists. Please keep doing it. Please keep making them know and understand the importance of science, mathematics, engineering, to our physics particularly, and chemistry, to our future. All the very best tonight. I hope that you find it a really interesting evening, and I hope that I can be back again soon in the not too different future. So thank you very much.
So good afternoon, good evening. I hope this works, and we are switching now to slides. I hope you can all see them. If not, please by all means come a bit forward. Let me thank you first to speak after the Minister. Fantastic opportunity. Thank you very much. Let me thank again the 4 societies: Teachers Guild of New South Wales, Australian Institutes of Physics, Royal Society of New South Wales. We had a terrific 200th birthday anniversary just last weekend for those who were there, and also Royal Australian Chemical Institute. Now I gave you a title which is a bit maybe complex, from botanists and butterflies to populations and planets. I will disentangle that as we go along. In fact, what's that?
Good alliteration.
the botanists and butterflies will actually be done in the first slide already. So we will talk about populations and planets, and we will talk about food and nutrition science as we go through the talk. Another point I want to make, you see I'm at this, I was invited, and that maybe has not become really clear from my abstract, to talk about biology. So I will talk about biology, but I am affiliated with the School of Chemical Engineering. So that tells you something, actually. That tells you something, and the point is really that biology is growing into all of these fields. And that's really the point I want to make. Another point I want to make is that you go home to your students and pupils in your schools and affiliations, and you tell them, go study food science at UNSW. If we manage that, it's a big success story. Okay, so I told you the next slide, this works. Next slide shows really that biology, like all sciences, is really a discipline coming of age, where we started out, I love this very much, this is a German painter, Karl Spitzweg, where we went from empirical observation, where we just look at stuff and are amazed, like this guy seeing these big blue butterflies, or also Leonardo, who painted or drew flowers. This is something biology students still do today. A lot of drawing and empirical observation of life, of things in our living biological environment, right? So this has changed. And when I say a discipline coming of age, we're talking about biology is going from being analytical to becoming very much synthetical. So we're not just looking and studying, we are starting to build things. And that is the reason why I really enjoy being in the School of Chemical Engineering, so that we can build stuff. Okay? And traditional areas in biology are metabolism, genetics, evolution, diversity, behavior, ecology, and so on. Nourishment of the system is key to all of those. You want to look at how things are being energized, what drives the metabolism of these things, how is energy taken up, how are building blocks taken into these systems to give them life. Okay? Good. Next slide shows basically an observation over the past 200-300 years. We learned that more calories will actually not add more years if we go along into the future. So for 200-300 years, we could give more calories into a society, into a population, into ourselves, into our bodies, and we would live longer. We would have a longer health span. We're talking about health span. Now it's becoming very obvious. Let me just see. This does not work. Now it's becoming obvious, if we put more calories into our bodies, like extending this dashed orange line, we will actually shorten our life expectancy. This is due to diabetes, to obesity, to metabolic syndrome, all of these things, or also Alzheimer's disease, which is known as type 3 diabetes. And the idea therefore has to become, what is it, how can we deal with food in order to provide better food, better calories in order to extend our lifespan? That is when by the end of last century, about the term of functional food has been developed, and when people started to talk about functional foods with a benefit to there's a question?
Have you explored the issue of fasting?
Oh yeah, fasting is a big issue, yes. And by all means ask questions. Yes, fasting, intermittent fasting is a fantastic, important topic. Still, we need to of course also shape the stuff that we put into our bodies. Right, so fasting is, I can talk a bit about fasting, maybe in the round table, but that is definitely an interesting, and then you can also look at physical exercise together with the right food and or fasting will put you in a situation where occasionally 1 + 1 is not 2 but 3. So super interesting topic. If we now say more calories will not add more years, we are starting to come to a dilemma, which is basically our population still is about to grow. So by these are figures and numbers everybody knows by now. By 2050, we will be 10 billion people on this planet, and we will, due to the increased socio-economical status, need to provide more calories across the globe, across all nations, across all populations, across all societies. So we are in a situation where we need to, in order to have food security, we need to have more calories, but we need to channel and control and provide better calories into the individual or also into societies and markets to drive sustainability, individual health, planetary health. So I will often use the term planetary health and sustainability equivalent in order to get this going. So this is a bit of the dilemma we are facing in food and nutrition science. At the same time, speaking of health, we know, and this is just a slide that shows the different risk factors. We know that basically 6 of the top 11 risk factors drive the global burden of disease. So by now it is all related to food and nutrition, not only individually but also planetary, what drives health and sustainability. Now, and here you will see now in the next slide that I've been for quite a while with the food industry. What can we do? How can we drive nutrition in order to achieve benefits? And this is non-exhaustive. There are many ways. Clearly, diabetes, metabolic issues, obesity, all are this big complex of, again, metabolic diseases where we can do a lot with nutrition. Less sugar, less salt, you name it, all of these things. At the same time, there is sound evidence, and we know that, for example, and this is not only for females, this is for males as well, skin health, beauty, external appearance can be addressed through nutrition. Wouldn't we all like to be like Granny here, fit and healthy and cognitively alert? And most importantly, proper nutrition is really something which we need to give to our children in the first 1,000 days. That is exactly almost to the day when you are reaching your second birthday, counting the in utero days as well. So the first 1,000 days really determine if a human being has a long health. So you rise high and you glide for a much longer time if you get that right. So we're talking about cognitive reserve. So there are many areas where this exploding field of food and nutrition science as a subsection of biology is going to thrive and is thriving already. And this is what we're trying to do also at TGNSW, as you will see in a second. The field as such, and here is my other frontier. So I realize, and Frederick, where is he? So you mentioned my affiliation with Frontiers in Nutrition. So there's this other frontiers in my life, and then there's this Frontiers here today, right now. So with the Frontiers in Nutrition editorial board, we've been sitting together and we've been looking at a de novo, from scratch analysis of what are the key pillars in our research field, in our scientific field. Very clearly there is health, individual health, driving food and nutrition science. There's sustainability, planetary health, which is becoming a really important topic. All of the agriculture is or in all of the climate discussion, agriculture is the biggest culprit, if you will, underlying the problems we're having. And it's not transportation. There's a lot of nutrition physiology, and I'm not sure if you can all read this, but there's exciting science looking into the gut microbiota in our gut. What are they doing? What is their role? By now we know they might be involved with emotional questions, with our brain health and so on. Organs on chips, you name it. There is clearly, as a pillar in food and nutrition science, everything that makes sure and provides food on our plates at home. So there is agriculture, very clearly. There is the entire food industry, and there's also home cooking. So home cooking is part of, if you will, the industry in small at home is home cooking. And then, and this was interesting and is different from physics and chemistry, I would argue, being in this whole food world, nutrition world, we need to be careful with evidence-based communication. We need to drive evidence-based communication. If you are in computer science, this might be different, but in food, everybody has an opinion, so everybody knows something. Everybody has an experience. We have bloggers, and we have many people who sort of speak up and do something online or in the newspaper. It is very important that there is a control, or that there is a way to make sure communications are evidence-based, are following a clear scientific principle, so that policymakers, like our minister here, for example, can come up and work with the regulatory bodies in order to come up with dietary recommendations. And that is what communities live upon, and good and healthy and important dietary recommendations. So we claim for our field really that evidence-based communication is a part of the science. Okay. Now to become a little bit more specific and to show you what we're trying to do at TGNSW, we're looking at food systems. What you see here is a food system, and the food system is really including everything. So from the green agriculture to the livestock agriculture, possibly directly from the green agriculture into the industry, then to the retail markets, to consumers picking up their stuff and to then eating and ingesting it either on the go, by themselves, alone, with their family, what have you. We all need to eat, right? What you see as well are those red asterisks that I put here, and that's where it becomes interesting. That's where it becomes also interesting for scientists and for engineers, because those are the problems. We have problems related to green agriculture, like arable land use. Is this done well? Is it done managed in a professional way. Water balance, a lot of water is being wasted and not used well. There are countries doing it better than others. Livestock, this list is again goes on and on. We know there is issues with livestock, food security, food safety, and we have seen this with COVID, that in factory farms, all of the infections really went up. Animal welfare, and I love a good steak. Just to make that point also already very clear, I love a good steak. So animal welfare, environment, and again, there's a lot more. I put in the center of the whole food system, I put food waste. Food waste is something which occurs along the entire value chain, and 30% of our food is being wasted. And that comes from everywhere, and is a real problem. And plastic and packaging materials, as you probably know, or as you maybe don't know, I will tell you, all of us, all of you, me, ingest or eat the plastic amounting to 1 credit card per week. Every week a credit card in our mouth, so in terms of microplastic. So that's scary and is a big problem for the environment. So now you can look at this all negative. We as scientists, as engineers, as chemists, biologists, we go and see opportunities. These are opportunities to do science, to do engineering, to solve all of these problems, right? And what we are doing at TGNSW, we're looking at meat. And I told you I love meat. So we're looking at meat. We're driving a new technology called cellular agriculture, or we're trying to drive this. And what you see here is a little bit data behind this interest in cellular agriculture. So very clearly, global meat consumption continues to increase. And we are growing, our populations grow, so people want to eat meat. And meat is really a good nutrition. Meat is good. Meat is nutrient dense, is healthy, has all of the minerals. I can tell you a lot about the goodness of meat, so why not? But we just need to make sure we get it right at the level of our planet, at the level of health, at the level also of animal welfare, and so on and so forth. So what is evolving is this area of cellular agriculture. Funny enough, this goes back to none less than Winston Churchill, who in the 30s of the last century made this statement, and now everybody's making this, and there are also here in Sydney, there in Australia, there are people. So the statement is really, we shall escape the absurdity of growing a whole chicken in order to eat the breast or wing by growing these parts separately under a suitable medium. So quite a visionary and quite a good thought. And then in 2013, to fast forward a little bit, a Dutch guy, Mark Post, actually in London, sort of initiated a big media event that has been sponsored or had been sponsored by Sergey Brin from Google, where they produced one patty to split the patty on a burger with the press, with the media, with cameras and so on, at the cost of about, I don't know, $700,000. But that was a proof of principle and super exciting and interesting. And ever since, this field sort of is taking off, and people try to follow up, mainly in small entrepreneurial startup companies, and hopefully so. And that was for me a reason to come from Switzerland here to also do this on an academic level, and to interact with students and the universities to get this going, because there are many problems. The very big picture, to give you a few technical details, the very big picture is the following. It took us millennia, it took us thousands of years, and we're talking about the Neolithic revolution. It took us thousands of years to turn from hunter-gatherers into what we are today, by putting fences around our animals, by making monocultures of wheat and grass. And we're talking about domestication. So things had been domesticated, but what has been domesticated is always multicellular stuff, if you will. So plants and animals. If you look at all of biology, and if you sort of look at the very big picture, even and also maybe in a historical way, you see that all these organisms, the kingdoms of biology, they either occur as unicellular, and bacteria only occur as unicellular organisms, not as multicellular. Fungi already, and we know this, occur as unicellular. We use that for beer, or they occur as multicellular, and we use that for, we eat champignons. Algae is similar, only for plants and animals. We are actually only exploiting and using the multicellular forms of these things. And then if you think back of what Churchill said, maybe there's really a way to populate these things, to develop technology that allows us to really grow tissues in a vat, or in vitro, as we say, in vitro, to boost this second domestication and to then address many of the problems we are facing. Okay. Now, a bit more specifically and a bit more sort of illustrative what is being done in the case of meat. And maybe if I just go back, we don't have to only talk about meat when we talk about cellular agriculture, because there might be interesting applications also for plants. But if we look at meat, the idea is to take a biopsy from a living animal that is not really painful. That's like plucking a hair. That's what people always say. You sort of take this biopsy of cells, you put it into a bioreactor, and eventually you sort of grow it. You put it onto maybe a scaffold, and there's many individual small technological problems to solve. But by the end of the day, and you do this scaffolding thing to impart three-dimensionality, texture, taste, all of these things that we love about meat. And eventually the hope is that we will be able to grow meat in a dish with a number of advantages. I show you in the next slide. But again, also with a number of problems, and those problems need to be solved at UNSW. So that's what we're trying to do, serum replacement, to scale things. A cow lives for 5 years, then it's being killed, then you make a steak, and you have I don't know, half a ton of material. To do similar things indoors is a whole new challenge, but it has advantages, and there are good reasons, and I will not go into all of those. There are good reasons to pursue this, and we're trying to really establish this as a third way. In the future, we are seeing traditional meat, we are seeing plant-based meat, and we are seeing these cell-based meats. And the idea is to drive benefits along health, sustainability, and economy at a minimum, as listed here: food security, allergies, contamination. At the same time, also to possibly reconnect again with vegan and vegetarian consumers that have gotten lost to the meat business, right? And again, animal welfare, biodiversity, greenhouse gas emissions, big time, with the idea to produce materials that are meat, and there's no question about that, in a way that does not necessarily always involve the killing of an animal. So that is a little bit the idea. I will stop here talking about my subject. That was not the idea. I wanted to show you what we're doing at UNSW. I want to go back talking about the bigger picture of food science and technology as a part of biology, and what we're doing with Frontiers to really bring this now on the bigger stage. What we're doing with Frontiers in nutrition, we meet every now and then, and we're trying to really set a global agenda for nutrition science. Where is this field going? And then we publish this. And that's very small here, and not you should not read that. But the point is really we're a global set of experts all over the world. We get together, and what we find if we look at our discipline is that food and nutrition science, 2015 to 2020, some of the key problems were sustainability, functional food, and so on and so forth. What we discovered, in a way, just by coincidence, 2020, 25 was about the vulnerability of our food systems based on COVID, how things are really in a very fragile state when it comes to feeding the world. And therefore, it justifies to drive a whole science in by itself. To then bring this to an even higher level, you all have heard about the SDGs, and it is FAO itself that is putting this into context, how nutrition science is serving all of the 17 UN SDGs. I guess you're all familiar with the sustainability development goals. So this is an extremely useful matrix, the SDGs, and again you can look that up online. But SDG 14, life below water. Fish gives 3 billion people 20% of daily animal protein. Climate action. And this is again, climate action, we always talk about aviation industry. Aviation industry contributes 2% at the most to greenhouse gas problems. It is the agricultural sector that contributes 14.5%. So it's much, much more. And that might be this point here. Agriculture is key in responding to climate change. And that is how we like to drive this field forward. Now, I want to really be as inclusive as possible, and want to just touch upon a few additional points, and I did touch upon them already, just because those numbers are interesting, and that's a slide I got from FAO, also from Lady Ann Tutwiler. Over the years on this planet, I should say, there's about 400,000 globally identified plant species, 400,000, of which about 5,500 are somehow useful, edible, and can be used. Why on earth are we only using 15? That's a very interesting question, and very clearly things might look better with regard to health and also planetary health, so both health and even economic health, if we would play this a little bit smarter. Interestingly enough, you can show that by having a more diverse diet, also your gut microbiota again are becoming more diverse, which makes sense, and driving a more sort of all-around health into your system. Another thing I want to show is food waste. I've been talking briefly about food waste already. We have every now and then, so we are in good contact with OzHarvest. We have Ronnie Kahn give guest lectures, also at UNSW. Food waste, a huge problem. If we can control and manage food waste, many of the other red asterisks I showed you and problems that we're having would disappear automatically because all of the food waste is gone, and because we would be able to manage the whole thing. So the challenge here is to avoid it or convert it into supply chain. And since I told you my wish is, or I hope that you all go home and that you tell your pupils about UNSW, I would not want to finish here without showing you something about UNSW. What you see here is actually the science engineering building, and it's no joke when I say she's on my neck. So this is my office, and then Martina, right, who will be our next speaker. Martina's office is up here, so I saved you a slide, I guess. And this is a brand new building. This is the Hilmer building. This is the science and engineering building. But what we've been doing over the past 1 or 2 years, we've really beefed up not only our facilities. We have amazing cell culture devices that came in very handy during COVID, because you can do tissue culture from home. You can log into the microscope and look at your cells and move microplates around and do all of this without being on campus. We have bioreactors to try to grow materials into reasonable amounts. We're having then, if all of this works, and once all of this works, already a pilot plant available of certain pilot plant rigs, and we're ready to beef that up more. There's an experimental kitchen to then do all kinds of things that you would do also at home maybe, but that can be done in a semi-industrial context. And finally, we have sensory science, which in Australia usually only happens behind closed doors of industry. So here at UNSW, we are open to all of this, and I'm not going to show you I'm not only going to show you the facilities. I also like to show you that we've been using those 2 COVID years to diligently beef up and improve dramatically our entire food curriculum that we're offering to students. So if your kids or students are interested in that field, I'd be more than happy to show more. The curriculum is really adapted to the 21st century, to all of those questions that I've been discussing here. And I'm not sure about the time, but this is my last slide. So thank you very much. That's been a lovely evening here. And if there are questions, please go ahead. Thank you. All right.
G'day, great to be here. I think I scared the minister off. He knew I was getting up and he thought it was just too heavy for Friday night. But I'll keep it simple. I'm delighted to be here, delighted to get a call from Fred yesterday. I'm stepping in for Andre Morello. I'm coughing, that's just nothing going on there. But I'm good, and I'm going to talk about photonics. Let's see if this works. I should be at a Rabbitohs game, of course. For those that know, the Rabbitohs game is about an hour away, so we'll see. I have a number of hats, so a little bit about me. My main gig these days is Director of Sydney Nano. This is the university's flagship multidisciplinary institute on the campus of the University of Sydney, and if you're on campus, please drop by and I'll show you around. Fabulous facility, fabulous example of multidisciplinary research. I'm also co-director of the New South Wales Smart Sensing Network. This was set up by the state government, sponsored by the Office of the Chief Scientist about 6 years ago. Susan Pond is in fact chair of the board and has been since the early days, since the beginning. It's a translational network that brings together universities to collaborate to translate smart sensors into solutions to some of the key challenges facing society. And I'm also a researcher in the School of Physics, and my own research is on photonics naturally. And these days I spend a lot of time working with the defence, the military. I was just in Canberra at the Air and Space Power Conference Monday, Tuesday, Wednesday, which was fabulous. And this is the launch of the Jericho Smart Sensing Lab, which is sponsored by the Air Force. And we've got Paul Scully-Power, Australia's first astronaut, Darren Goldie, who's Air Vice Marshal, Duncan Iverson, who's our Deputy Vice Chancellor of Research. But tonight I'm talking about photonics. So what is photonics? So I'll start at a high level. I know this is a broad audience. I recognise a few people, but I'll keep it simple. You all know electronics is the building block of computation, computers, microchips in your smartphone are providing breathtaking computational power built around electrons, and photonics deals with light waves. Of course, light waves are made up of photons, but when we consider photonics, we typically consider a wave picture. We have the electric field and the magnetic field, as you would probably remember from high school. Photonics is about as old as the invention of the laser, which was the 1960s. And of course the laser is the enabler of communication systems, the internet, and that's transformed our world, and I'll explain in more detail. And what I'm going to focus on is kind of an interesting convergence, because we've come back full circle and a paradigm shift has happened in the field that I think it's fair to say we have played a key role in driving, and that is to bring photonics onto a chip and potentially to marry that photonics with that electronics, and I'll give you some examples of why that's really exciting and challenging. So to give you a historical perspective, I like to say to my students, we sit on the shoulders of giants. This is a 150-year perspective. Everything I'm discussing builds on Maxwell's equations. Now, Maxwell's equations are, for me, the most exquisite equations that have ever been derived. They describe how electromagnetic waves interact with our world. They are still completely accurate and robust today. They govern electromagnetic waves, optical frequencies, microwave frequencies, X-rays. Beautiful set of equations. Having a diffraction limit in the town of Vienna, or the city of Vienna in the former East Germany, a beautiful place where modern optics was born, and the concept of diffraction is a key part of our world. And of course, if we look through the last 100 years, we kind of recognise some key milestones. Einstein obviously played a key role in terms of general and special relativity. The maser was then introduced in the 50s, and it was the precursor to the laser, which came along. Ted Mayman didn't win a Nobel Prize, should have. And there were lasers associated with a number of breakthroughs, but not Ted. Lasers were initially a solution looking for a problem. They dabbled with lasers in medicine. It's interesting, that's such a hot topic now. And of course, then optical fibers were introduced. Charlie Cowell, who did win a Nobel Prize in 2009, at the age of 75. It was a little bit later in his career, about 40 years after that invention. Communications, as I said, photonic chips have come along. Smartphone optics are a huge area of industrial investment. And just to wrap up this historical perspective, gravitational waves were detected 5 years ago, exactly 100 years after the prediction from Einstein, and that was all about lasers. So lasers and photonics is in fact a massive part of our world. This is from a US National Academy of Science report a decade ago, and it says the linchpin, it's the linchpin of a $7 trillion industry. If you look at 7 trillion, your instant reaction, 7 billion, oh, $7 trillion, what? So if you had not available lasers, you would have no internet. You would have no e-banking. They would collapse. There is no alternative. So it's a pretty significant part of our world, pretty significant part of our economy, our industry, and it is continuing to play a vital role in other areas that I'll allude to, particularly defence, national security, as I've hinted at. But of course, what has driven photonics as a science, as an ecosystem, is the explosive bandwidth demand that we all thrive on in our homes, in our lives. Just to give you some basic factoids that you've all seen before, data is doubling every 18 months. That has happened throughout my life. It will continue to happen. I have had many conversations with people where someone will say, but surely it has saturated. There's nothing left. What possibly could be on the horizon? Now those conversations were 30 years ago, 20 years ago, 10 years ago. There's nothing special about this point in time. It will continue to grow. Hundreds of exabytes per month of data. Mobile data traffic 20-fold over the last 5 years, factor of 100 every 10 years. Billions of devices are added every year. And of course, it's been driven by the social apps and streaming. I worked out the other day that in my house we have 7 subscriptions: Disney, Amazon, Apple, Netflix, Stan, help me, there are 3 others.
Amazon Prime.
And we're going to say Amazon Prime, that would be in the top 3, but there are like 7 apps, streaming services. We don't watch TV. Who watches TV? My kids haven't watched TV for 10 years. It's YouTube. It's just sucking all this bandwidth. So the Internet of Things is now with us, and it's a really important part of our world. And of course we have the NBN. Wow, I actually met Mike Quigley the other day, who was the chief of the NBN. He had some strong opinions. It's really interesting to talk to Mike Quigley about what went wrong, not implied that he suggested it went wrong, but you know what I mean. We have the NBN, and it's okay. We are still not even in the top 40 countries in the world, and it has a long way to go, but it is essentially our optical fibre communications network, and it links the cities, the towns, it provides the bandwidth that we thrive on, and it's all based on photonics. At a global level, optical fibres are wrapped around the planet many hundreds of times. We've literally laid billions and billions of kilometres. At some point, at the peak of the bubble, this was going back 15 years ago, we were making optical fibre at Mach 2. And then sort of crazy little factoid, but that's a true statement. That's the rate at which we were making optical fibre to deploy around the world to meet the bandwidth demands, the growth in bandwidth. So this optical fibre is everywhere, it's ubiquitous, it's had huge impact on a society. And I like to simplify our understanding of optical communications by using a familiar analogy, which is that these light pipes, as they are referred to, are really the information superhighways that connect the cities, that transmit the data at the speed of light, or at least the speed of light divided by the refractive index, And what we are dealing with often in our research is not the actual light pipes. They're relatively straightforward to make because they're optical fibres. It's actually the getting the data on and off. It's the kind of the router that's the problem. It's the switch, isn't it? It's the kind of this situation here, and it's avoiding the collisions, the crash that you run into. And I had 3 experiences on the way here as I left the university, and my wife dropped me off on the way to the Rabbitohs game along Parramatta Road, which was a bit of a nightmare. So I hope that gives you a simple picture of what it looks like. One of the emerging issues that we started to grapple with in the context of that massive increase in bandwidth, deployment of photonics, deployment of lasers, was surprising that it turned out that optical communications networks, routers in particular, are significant consumers of energy. Who would have thought? It is kind of breathtaking if you actually think about it. Every time you Google a computer on the other side of the planet in a data center is doing a calculation, and actually if you add it up, routers are significant contributors to emissions. They require more energy than the airline industry. Okay, simple statement of fact. I mean, it's growing pretty quickly. And so it wouldn't surprise you if I said data centres that exist all around the world, in Australia, in Sydney, but many of them are in North America, in China. They like to build them in the Arctic. They put them under the ocean to cool them put them near a dam, because they are incredibly hot, energy consuming. So lots of challenges, and I'll come back to that. Now, photonics, as I said, is the linchpin of a $10 trillion industry. Going forward, it's going to play a vital role in a number of key areas: resources of the environment, life sciences, security and defence. I'll give you a little bit of a hint of why photonics is so vital to some of our domestic national defence partners. Automation, sensors, infrared optical sensors, neuromorphic sensors, and smartphone optics, as I alluded to earlier. So let me give you a little bit of a flavour of the science that we are doing at the University of Sydney to address some of these grand challenges as it relates to bandwidth, energy efficient communications. This is a simple kind of construct here, but this is a typical laboratory experiment. That's a photo taken from Google Images. I've just put into Google optical physics experiment, and I've downloaded an image. But that's an experiment. It looks like my PhD thesis, actually. And on that table there are lasers and modulators and detectors and diffractive elements and switches and all sorts of components that are the building blocks of any optical system of communications network. What we're doing at Sydney is we're putting all of those components onto a chip. We're printing those bulky components that are heavy, this might weigh a tonne, onto a chip that is thumbnail size. We're using the lithography techniques that have been developed for the microelectronics industry in particular, that we now have in Sydney at the nanoscience hub that I'll refer to in a moment, to print at a nanoscale photonic circuits. And on these circuits we have lasers, we have light sources, we have detectors, we have modulators, we have switches, we have all of the building blocks to create this revolutionary photonic chip that provides bandwidth processing and massive reduction in energy consumption, and I guess in the language of defence, size, weight, power, as they refer to it, SWAP. So these chip-scale photonic electronic circuits that we'll be talking about, and I'll wrap up soon, provide a massive reduction in size, weight, power. Importantly, we get bandwidth, we get low latency, and we get that key advantage of energy that I referred to. So these photonic chips are really this new paradigm that we've introduced in this new information age. They're faster, smaller, greener, smarter. Initially focused on the green bandwidth problem that I've already alluded to. We find now that these photonic chips are playing a really important role in other areas. My team has worked with companies like Lockheed Martin, L3Harris. We work with Air Force on utilising photonics to enhance next generation radar, satellite communications, next generation 5G, 6G. It turns out there's photonic chip technology where I can integrate thousands of photonic components onto a chip is in fact the building block of a quantum processor. It's interesting that the leading companies that are attempting to commercialize quantum computing in the US are using photonic chips. One of those companies is in Silicon Valley, and it's actually raised about $1 billion. Jeremy O'Brien is an Australian, he's the CEO. Another company in North Chicago, and they have hired about half a dozen of my former PhD students, and they're also using photonics to build a quantum computer. And then finally, photonics is playing a really key role in sensors. So photonic devices that might integrate even into your smartphone that can sense the air, might sense and detect the blood that reveals your health condition. Okay, a little bit more detail to tell you the true story here. So we are, to a large extent, when we think about these photonic chips, we're going to leverage silicon. A ubiquitous material that is the basis of all micro and nano electronics. And as an interesting factoid, if you were to crack open your smartphone, and I don't suggest you do this, and pull out the microchip that's in your iPhone 11 or 12, I think we're up to 11, aren't we? Look under an electron microscope, 12. The components that are the logic operations on that chip are of order 10 nanometers. 10 nanometers. And so that chip has of order 5 billion. You're reaching into your phone right now. He's going, you're kidding me. I'm going to check. Of order 5 billion components in your phone. Again, that's just amazing. That's Moore's law for you. So we are leveraging that same silicon technology to build photonic circuits. And companies like Intel have IBM, sadly, and National Labs, IMEC as Europe's major microelectronics foundry, have invested billions of dollars in this. AIM Photonics is a US defence consortium, and in Australia, the Nanoscience Hub, the clean room that I alluded to, is providing that capability. So what does it look like under an electron microscope? This is an example of what we call a planar waveguide. You're looking through an electron microscope, and that is a rib. It's about 500 nanometers in width. The light is confined in that rib by total internal reflection, which is a concept that we are told in high school, and propagates along at the speed of light. And we are able to manipulate and create structures and components at the scale of less than the wavelength of light. Examples of ring resonators, photonic crystals, metamaterials that have optical properties that are unique, unavailable in nature. Metamaterials are the basis of cloaking technology, which you've seen in James Bond movies and so forth. And I guess to wrap up the narrative, I'd like to think that we are early on in the journey. It's only 20 years old that photonic chips started to be manufactured. How long did it take microelectronics to evolve from the very early days to where we are now, where we literally have 1 billion components in our smartphone? And what will the world be like when we have that level of sophisticated photonic processing at our disposal? So I'm a scientist at the end of the day, so I sit at the interface of science and technologies, research and industry. This is a slide that talks to some of the achievements. Very proud to be director of the City Nanoscience Institute. This is back in 2016 when the hub was launched. My colleagues David Riley, Michael Bessick, I was on a flight to the US, upgraded in a United Airlines flight, and I'm sitting next to a lady who had this Herald article open like this. Have you ever had the experience where someone's sitting next to you and they're reading a story about you and you just want to nudge them? It's a topic that generates a lot of excitement in the media. It's a topic that gets published in the top journals. This is a science paper from a few years ago in collaboration with the Technion. And I'm pleased also to note it's a topic that attracts some very strong female researchers who are in my team who have gone on to take on important leadership roles. Andrea Blanco-Redondo is now Director of Silicon Photonics at Bell Labs. Birgit Stiller is a group leader at Max Planck and Erlangen. Let me just wrap up with a couple of examples, and this refers to work that my team has done with the US Army Research Lab, Lockheed Martin, Harris, and the little figure there kind of explains the context, which is developing photonic technology that can block a jammer, pretty relevant, F-35, actually F-22, if you really know your fighter plane business. This is a prototype that my group took to Army Lab and demonstrated this in Washington, DC. And that was a significant milestone, and that was the beginning of a significant engagement with Defence. In 2019, as I mentioned, Air Force, our Air Force established what is now a 7-year, $20 million partnership with Sydney Nano. In particular, my team on developing next generation sensors for situational awareness. Here we have Air Vice Marshal Darren Goldie. I spoke to Darren. He's now a 2-star, so he reports to the Chief of Air Force. And the reason they're interested in nanotechnology is the notion that it can be massively reduced in size, weight, power. It's kind of important if you're trying to put things in the sky. So this resonates deeply with them. When we had the launch, this was my idea as a bit of a stunt, I printed this logo onto a piece of silicon, and that's a human hair. And at the event, this is what we are holding in that photo I showed you earlier, I think. There's a little chip, and on the wall I had projected the light scattering off this chip, and I got the Air Vice Marshal to adjust the microscope, and it appeared on the wall, and there was this ooh-ah moment. It was a bit cheesy, but it just goes to show you. And again, this is a nice movie, but I don't think I'll play this. Here we are presenting through the Eureka Prize. My team was recognised with the Eureka Prize in 2020 for research that is providing safeguarding. This is the Minister Melissa Price. This is in the Messel Theatre. My colleagues in the background. And this is the photo where I think they're all pointing at the chip, which was a lot of fun. So I think on that, thank you very much. I think, Fred, stay around for questions and look forward to talking to you and enjoy your evening.
All right, hello everyone. I like to move a lot, so I'm going to pick up the microphone and wander a bit. I'm a little bit hyperactive. Thank you for coming tonight, and if you're watching this in the future, hello, thanks for watching. My talk is going to be quite different from some of the talks that you've already seen tonight, some of the wonderful talks that you've already seen. Mine is geared quite closely to teaching and learning within schools, and in particular, geometry. Okay, so I think everybody here can remember geometry. They might not be pleasant memories, but there will be some familiarity there. And there's also something a little bit different, because geometry is very old, right? 2,500 years or so. But before I get down to my talk, I do have this could be the most important part of my talk here. I do have free gifts for everybody. So what you're holding now is called a geometry template. And these have been around for 50, 60 years at least in this form. And engineers, designers, draftspeople, architects know how to use these, and they see great value in them. Now, the point of difference that I'm going to talk about today is using these for geometry and the teaching and learning of geometry in middle school or high school. Now, most of you will recognise this picture here of a compass. For the last 2,500 years, the compass has pretty much reigned supreme. You use a compass and a straight edge, which is basically an unmarked ruler, to do geometry. And millions of kids around the world learn this every year. You see it in the Australian curriculum, in Singapore, in Hong Kong, in the UK, all over the world. People learn how to do geometry. So the most interesting thing, I think, is taking a very old, familiar area like geometry and really looking at it in a new way with what's called a circle arc template. Okay, so a little bit about me. I'm, I guess, quite well known for early contributions to digital education. I started very early. Obviously, I don't look like this anymore, but you look back at these things and go, I don't look like that. Okay, but this is me. So one of my first videos, very amateurish. You can see the camera's not straight, the lighting's not very good, and I'm sure it was terrible, right? But I took a risk. Okay, and then about 10 years ago, I did my first live stream. Of course, with COVID, everybody's doing it now. There's me in my office, again, looking a lot younger. So, like I said, the topic of today's talk is about geometry, okay? And it's everywhere, right? And it goes back to the second most popular book of all time, Euclid's Elements, just behind the Bible. This book was written around 300 BC, and it's been in production ever since. At one point, it was a must-read for pretty much every high school student. Now, like I said before, traditionally there are two tools of instruction. One is this weapon right here called the compass, and the other one is a straight edge, which is like an unmarked ruler, okay? Plato from ancient Greece gets the credit or the blame for these two tools. You could not use anything else. That was it. This is all you had to do geometry with. A compass and a straight edge, okay? Plato objected to other tools being used. I think with Plato, he had a very interesting connection with geometry. He see studying geometry as getting closer to God. So it was almost like a holy experience for him. And any other tool was absolutely verboten, right? It was forbidden. Now, because we've been using the compass for so long, at least 2,500 years. It's just what we do, right? It's just what we do. We've always done it. When you were at school, I bet you used a compass, right? That's just the way we do it. So it seems fine. Like, why is there a problem? Well, try to think about the last time you used a compass. Was it a very pleasant experience? Can you even remember? Did it stick out? Compasses are terrible. They are terrible. I said it, Plato, I'm sorry. Compasses are terrible. Why? Because they're hard to use. I gave my 9-year-old son a compass. He had one hand on one leg, the other hand on the other leg, trying to... And then I said, oh, no, Louis, try it like this. Do you know how difficult it is to roll a compass between your thumb and your forefinger? It's very hard. You need fine motor skills for that. And then you try to produce a circle which doesn't look like a circle, right? The compass slips, or you stab yourself, or something, right? So they're hard to use, they're inaccurate, and they're like little weapons, right? So you probably can't see this, but this is a funny thing I found on the web, right? So try to draw a compass. Oh no, the compass is, draw a circle, the compass is slipping. That's the circle you end up with. I'll just trace around a coffee mug, right? Students do it. They trace around all sorts of things, right? Cut a line segment in half using the compass. Well, why does this look so wrong? Just eyeball it, just do it without the tools. This one, trace 2 arcs. You're trying to bisect an angle here, cut it in half. All is arcs, too many arcs. I can't control the arcs. This is the struggle that students of geometry face, and their teachers face every day. When I have given this tool and chatted about it with teachers, do you know what? Some of them say, Chris, I hear you. I've spent an entire lesson just trying to get our students to draw one circle. That is frightening. That is scary, right? Okay. Now, recently, there's some data to sort of, show the problem even more distinctly, right? There was a study done in Indonesia recently, and it wasn't just students who struggled with using traditional compasses, teachers as well, right? I don't know how you would use a compass like this on a whiteboard or a blackboard. What are you going to do? Of course it's going to slip, right? So it's not just students who have problems. 40% of teachers in this survey said that they have problems too. Now, this is extreme, but compasses are like little weapons. They have been used in bullying and even in alleged murder. Yeah. So when you compare that to the very peaceful circle arc templates, I don't know if that's going to kill anyone. Probably not going to eat it like the credit card, but yeah. Yes, question?
I've got a tattoo on my finger. You can still see the lead.
Oh no!
From a compass.
That's from. There we go. Thank you for sharing that. So you're at high school. See, yes. So please share your compass stories with us. Like I look, yes.
But remember, the compass has been mechanically designed for someone using paper, and it's the perfect instrument when the point goes into paper. It doesn't slip. So you're omitting to say it's technology that has disappeared with the computer.
That's a very good point. That's a very good point. I would prefer to do my geometry without inflicting all the holes on the paper. That's just me. That's just me. So with something like this, there's no stabbing of the paper. But I do take your point. I do take your point. The other. So let's say the compass doesn't slip. Let's say you have a compass like this one. Depending on how you turn it, the legs can flex while you're turning it, even if it's anchored properly. Again, you do not get a true circle.
Do the screws up so it doesn't slip.
But then that's a good point. Do the screws up, right? 2 minutes later, you have to undo it again and get it to a different setting, right? All right. So.
I didn't do DGD at school.
All right. So the point I'm trying to make here, as you can probably see, is that although we've been spent thousands of years with compasses, there are problems. Especially in classrooms. And so what might a better alternative look like? Well, I'm glad you asked, okay? This is pictures of the circle arc templates that you're holding in your hands. You might be familiar with this. It's almost like the crosshairs of you look through it when you're looking through a rifle, something like that. Yeah. this is helpful. You can do it like this. But the problem with the top version is that you cannot place the centre of the circle on a point, on a given point. You can't do it. And in geometry, as you would know, that's pretty important. The centre of a circle, that's pretty important, okay? So what we came up with, we spent a year on the design of this, was some of these prototypes. Now, in the middle, that shape probably reminds you of maybe an 80s game. Yeah, Pac-Man, right? Or Ms. Pac-Man, however you want to talk about it. It's got a centre point that you can put on a given point, right? So you can place it where you want to. And the arc is about 300 degrees. Now, when you look at it, you go, oh, Chris, that can't draw a full circle. So here's something that's interesting, right? Well, you can rotate it, of course, right? But actually, believe it or not, in geometry, in all the geometry that you see at school, you do not need to draw a full circle. You do not need to do it. To get all the constructions, all the points that are seen in all the curriculum, you do not need a full circle. You just need the intersections of points, circles and lines. That's it. So this is enough. And then people say, well, Chris, you can't adjust it. You can't make it bigger or smaller. Again, it's not necessary. You can do all of high school geometry with one opening. With one opening. People's minds get blown when you say that, right? This has been known for at least 500 years, but we don't teach it in school. We get people to open their compass, unscrew, close it, screw it up again. All right, so this is our new design down the bottom. Okay, here's a series of arcs. Again, you've got a centre point. They can be big or small, but one is enough. Okay. So what are some of the potential benefits? I'm glad you asked again. Templates are familiar to learners. Why? Because they're a bit like a ruler. Students tend to have not good experience, but they have experiences with drawing along straight things, like a ruler. And they also have experience in drawing around the inside of shapes. For example, on a template, they might be wanting to write letters or symbols or something like that. So it's actually quite familiar to them. That's the first thing. I would say that it's very easy to use. Why? Because the tool stays fixed. You don't rotate it like you do with a compass. It's the pen in your hand that moves, not the template. So I'll show you in a minute. There's no adjustments required. You don't need to open and close it. You get a pretty precise output, and there's no holes in the paper. And I think there's less chance of it being weaponised. I'm sure you could find a way. Students will find a way, but yes, it's not like a compass. And like I said before, it can do all the basic geometric constructions. Okay. All right. So, how can geometry templates be used for instruments of basic constructions, and what are the benefits and limitations? I'll talk you through that, but I actually want to show you how to use the tool. Is that okay? All right, okay. Let me switch over then. All right, so let's do a basic one. All right, so let's look at a starting type construction. Sorry if my head's in the way, I'll try to get down here. Okay, so one of the oldest ones is something like that, right? You've got a line segment, and what you're trying to do is to use the compass or the circle arc template and the straight edge to slice it in half, okay? Slice it in half. Now, you cannot change the size of the circles that you're drawing, but it's not a problem, okay? It's not a problem. So if I take actually I'll use the other one. If I take my circle arc template, which is here, and I centre it at one end, and I make a little cut, get a new point, and then I can put it at the other end, make a new point. Okay, we've got 2 new points. Great, that's what we do in geometry. Move it over. This time make an arc. Oh, my hand's shaking a bit. Okay, do exactly the same thing at the other point. Okay, 2 new points. Use the straight edge. That's it. Okay, that's not rock. That's it. You don't need pretty much every high school says, every high school textbook that I've seen says, oh, just open the compass at least halfway and do these things. You don't need to do that. You don't need to do that, right? So this is the same length as this, and the angle is 90 degrees, okay? Let's do one more because I'm running out of time. Okay. What about bisecting an angle? Okay, well that's when you have a given angle. Okay, let's say A, B, C, and you basically want to take that angle and slice it in half. Slice it in half. Okay, so what do you do? Well, this is not a problem. Put your center point of your arc at the corner. Get 2 new points. Then you use those 2 points, draw 2 more arcs, and connect them to your original point B. Oh, let me fix that up. Okay, so this angle is identical to this angle. Okay, that's how you do it. So, look, they're just a couple of things, and people are not easily convinced, especially skeptical scientists and teachers and engineers, and that's a great attitude to have because you need to put this under scrutiny, right? How can you argue with 2,500 years? Well, I'm trying. I think that's all I have. Please feel free to ask questions maybe when we have a chat with Ian Woolf. So just thanks for coming. Enjoy. If you don't have a template, just grab one, or if you want some other stuff, I've got pens and, I think I've got a couple of coffee cups and stuff. Anyway, just let me know what you want because I don't want to take it home. So, Fred, I'll pass back to you, and thanks for coming, everybody.
Thank you, Frederica, for the kind introduction. It's great to be here. So the last talk, I want to talk a little bit more about what other people are doing, not so much what I'm doing. And I want to convince you that nano is great and there's a lot going on. I actually saw here in the bathrooms there's a nano soap, so I was very excited about that. So, of course, maybe some people remember these headings in the newspaper: nano, a new hazard, a new asbestos. So everything's wrong with nano. And of course, maybe if you're sort of in the 90s, 50s science literature, you might even remember some of these books where you had little evil nanoparticles that come and invade the world, and there are just bad things about it. And so far, our attitude towards nano hasn't really changed too much, but I would like to convince you today there's a lot of great things about nano, and especially when we talk about nanoparticles in medicine. So as I said, I'm going to talk a little bit less about what I'm doing in my labs, but more about the field. I want to introduce you to the field and why this field is really exciting. So first of all, what is nano? So we saw already before a little picture of a hair and something nano next to it. And in fact, your hair is around 100 micrometers. So if you touch it, that's around 100 micrometer. When we talk about nano, we talk about something that's around 1,000 times smaller. And then we are really going into the world of viruses. Viruses around sort of 50 to 200 nanometers. So we're going very, very small. So the question is, can we actually see nanoparticles? And this is sort of a typical beaker with water and a lot of nanoparticles in there, and you can't see them. So that's a little bit scary, not knowing what's really in this beaker. But science has enough techniques to really make these nanoparticles visible. And actually, you're sort of a little bit familiar with some of these techniques. So just go to your dusty shed or your dusty attic, or maybe on a nice Sydney morning where the pollution is ripe. You see how light scatters on something in the air. And if you turn off the light, it's gone. And we use the same concept. We use lasers to basically make these nanoparticles visible. And from there, we can basically tell how big our nanoparticles is. But nothing really beats a good photo. And we saw already before some beautiful photos taken by a transmission electron microscope. And that's not your little light microscope. It's actually something big and can sort of fill up a room. But the beautiful thing is you can now really see your nanoparticles. So you can go down, you see your viruses. And so we see now enough about the coronavirus. But of course, we know that the coronavirus looks like that because of microscopy. So nanoparticles in medicine, they found a lot of application from drug delivery, imaging, sensing, blood purification, tissue engineering, and maybe even nanorobots, but that's more sort of a future vision. I would like to talk about drug delivery. That's sort of the field I'm very passionate about. So the problem with traditional drug administration is that when we get our drugs injected, they go everywhere in your body. So they don't really go where you want them to go. And it's depending on the kind of treatment, but for example, in cancer, only 1-2% of the drugs that get injected actually reach the cancer. So 98% are excreted by the kidney. The rest, there's a lot of damages around your body, so you lose your hair and so on. So it's very undesirable. We need to inject more and more drugs to really get the effect in your cancer. So that was sort of recognized very early on. And there's a concept by this gentleman here, Paul Ehrlich. He said already in around 1900, wouldn't it be nice we have a magic bullet that can treat all the diseases? And what does a magic bullet look like? It, for example, has some sort of pharmaceutical carrier. This was the time before we knew much about nano, but he had sort of this vision about something that carries something around your body, like a little plastic bag for drugs. Inside, we put a lot of drugs to make it a really good, efficient bomb. And then on the surface, we put something that helps us to deliver this magic bullet. And this is now a concept that's widely explored in research in the clinic. And we're really there now that we can really realize these concepts. So how do we use nanoparticles for the treatment of cancer? Or why would we want to do that? The first one is the protection of drugs. So a lot of drug molecules, and the most famous recently one are mRNA drugs. You would not be able to deliver them in the body without the help of a nanoparticle. So sometimes you want to increase water solubility. A lot of drugs in labs are actually discarded straight away because they don't dissolve in the bloodstream. They sort of precipitate out, float around. But the biggest issue is you would like to maintain it in a so-called therapeutic window. So the typical issue is you get your drugs injected, and very quickly it's been cleared from your body, and then after 8 hours you need to get another injection, you need to take another pill. So the idea is now we only get one injection and your drug stays in your body for a longer period of time, like a little reservoir. But most of all is we want to target the drug to a certain site in the body. And I think that picture on the side here sort of summarizes the idea that we have now these green nanoparticles, and somehow they find the tumor or the diseased site. We bypass drug resistance as well, and at the same time we can see where these nanoparticles are. We can image that, and we can't image drugs, unfortunately. We don't know where the drugs are. So there are a lot of nanoparticles out there. Some are good, some are not so good. So we have some that are great for diagnostic devices, for example, for your red test, but they're not something you really want to have in your body. there are other nanoparticles that are used to treat cancers. And these are sort of what I would like to show you now, what kind of nanoparticles are actually used. The type of nanoparticle starts in what kind of sizes you have. So we can really go down from 5 nanometers up to 1,000 nanometers, and they all have their purpose. So how do we get now nanoparticles to deliver drugs? So it's actually a long journey. It's amazing that we have nanoparticles on the market, and they work. And I just show you that these many obstacles these nanoparticles have to go through. So the first thing is we need to somehow take our drugs and our nanoparticles and put them together. So it's a little bit like magic. That's where people like I come in. That's what I'm doing for a living. I try to convince them to somehow go together. But then we inject them in a bloodstream. And so in the bloodstream, there's, of course, blood cells, there are proteins, there are other things. And on this point already, a lot of nanoparticles get cleared. And they get cleared because in your bloodstream you have a lot of immune cells, and the immune cells see, oh, there's an invader here, we need to get them out. However, if we're lucky enough, they circulate around the bloodstream long enough, and now they're past the tumor. So once they're past the tumor, they can very quickly diffuse into the tumor. And the reason why they do that is because of the way tumors are formed. They have a very ill-defined vasculature. But in contrast, nanoparticles don't really go into healthy tissue very well. So once they're now in the tumor, the last step is they need to go into the cancer cell and unload the drug there. So we have here now nanoparticles in front of the cancer cell just waiting to get in. And we just wait 5 minutes, and you see how on the right side all these cancer cells light up because now there are nanoparticles inside. So once these nanoparticles reach the cancer cells, it's actually relatively easy to get in there. The journey before is the challenge, really. But nevertheless, we have a few nanoparticles on the market, but just to show you how long the journey is. So we usually have many years of preclinical trials where we really look at a drug problem and we try to design a nanoparticle around it. Then we go to phase 1 clinical trials, usually with just 15 or 20 patients. Then phase 2, phase 3, and then phase 4 clinical trials. And just to give you an idea, when we have something on the market, we usually have around 40,000 drug compounds that were tested. So it's not a lot that's left at the end. So it's then pretty amazing that we actually have drugs on the market. And we also have nanoformulations on the market. And the very first one is Doxil. And so Doxil is a formulation that's widely used. And this was the problem. Doxorubicin was discovered, great drug for a whole range of cancers, but it has terrible side effects. Cardiotoxicity is one of the most significant ones, and of course all the other ones like losing hair and so on. So it was now a challenge for Professor Bernholz here, and he actually said there's 3 issues we need to address. The first one is we need to design a nanoparticle that's not detected by the immune system, so it circulates around your bloodstream for a long period of time. The second is we need to get a lot of drugs inside this nanoparticle to make it really like this magic bullet that is really toxic. And the third one is we need to get these nanoparticles to go into the tumor, and they need to be there, and they need to really accumulate. So I showed you already there are a lot of nanoparticles we can choose from, but the most common ones that are on the market, they're called liposomes. And liposomes are based on molecules that have 2 parts. It has a part that's quite hydrophobic, it really likes oil, and another part that's hydrophilic that likes water. So it's a little bit of schizophrenic molecule, doesn't know what to do when you put it in water, but if you put it in water, the following happens. It starts to self-assemble. And it can self-assemble in different things, but in that case, it self-assembles into something called a liposome. So these are now hydrophilic molecules. They are in water, you can't see them, but they have a little layer that is hydrophobic, and in the core you have a little reservoir. And so that's what this team did. They basically looked at liposomes and say, how can we reduce the uptake of liposomes in the bloodstream? And what they did, they put PEG coating on it. So the little molecule is a material you find in your creams, for example. It's widely used. They put a lot of drugs as crystals in the core, and they made the particles really small. And that's what they look like under the TEM. So then you start with something like that. You do a lot of preclinical studies. For example, does the nanoparticle enter cells? And just to give you sort of an idea, a cancer cell is maybe sort of 10 to 20 micrometer. Next to it are little nanoparticles, and they go actually in quite well. And so you can usually see how these cancer cells light up. Then is the cancer cells killed? What about healthy cells, mechanism? So all these things take years to really answer all these questions. Then you go into the mouse study, and you want to know in your mouse, where does actually these nanoparticles go? Where does the drug go? Does the tumor still grow? And once you're there, you can go into clinical trials. So by that time, you probably sorted around hundreds of nanoparticles out there just not working. But here, 1991 to 94, first clinical trial, they had 16 patients. So they looked at the distribution of the drug either in nanoparticle or as a free drug. And so when you look in the bloodstream here, the free drug was cleared after 24 hours, while the nanoparticles circulated around in the bloodstream for a long period of time. And then when you look at the tumor, you find here a lot of drug in the tumor, very little free drug. So that was fantastic, and so that was the first nanoparticle approved, and it's widely applied for a whole range of cancers, breast, ovarian cancer, a lot of solid tumors as well. Then another one came onto the market, Abraxane. So Abraxane is Taxol or Taxol, similar problem, not a very soluble drug, and it usually gets administered with an oil. And it caused huge side effects. So people did not respond very well to it. Here a chemical engineer came on board. So it's not a medical scientist, it's the chemical engineers, Johannes. So I said, well, it's really an engineering problem. We need to engineer something around it, a little nanoparticle. In that case here, the problem was we need to enhance the solubility. We can't use that camphor oil they were using before that caused all these side effects. And so Neil Desai and his team, they came up with a very nifty idea, because they said, well, let's think about what's already in our body, and we use that. And what we have in our body is proteins. We have a lot of proteins, and actually we have a lot of albumin. And your bloodstream is 7% protein, then more than half of it is albumin. How about we just take albumin and make a nanoparticle from it? And so they took the drug, they took the albumin, they processed it together, and they got a particle. And they called it ABI 007 because it's the license to kill cancer cells. So, and it was very good in killing cancer cells. So these nanoparticles are basically now floating around the bloodstream, and they slowly fall apart until they reach the tumor. And albumin also has another advantage, because your tumor actually sucks in a lot of albumin. Your tumor is very, very greedy, and it likes taking all the nutrition, likes taking albumin as well, does not realize with the albumin comes a toxic load. So again, we're going through all these studies, and that was certainly not the first idea they had, the first thing that was successful. Does the nanoparticle and drug enter cancer cells? Are the cancer cells killed, and so on? Does the tumor grow? And here just show you something about the very first mouse studies, where you basically inject a little tumor in a mouse, And you look how does the tumor grow over time. And you see, if you don't do anything, the tumor keeps growing very quickly. If you just administer a different drug, it maybe reduces the growth. But here's your RBW07. It has a license to kill the tumor. It was very successful. And the first clinical study with 63 women on breast cancer saw a significant reduction. And what was very important, though, is it was not that the formulation was so much more efficient than the free drug, but it was so much safer. There were so much less side effects, and that made it really important. And so there's still ongoing clinical studies on Abraxane for various tumors. The first one was approved for metastatic cancer. And it's the standard of care almost. So 600,000 patients around the world have already been treated with Abraxane. So my very last topic is delivering DNA drug, because this is very topical. And let's see if that video works. Because you're just wondering, why am I showing you something now on, oops, working. Oh, you can't hear the sound, but it doesn't matter. I just talk over it. So what you're seeing here is the coronavirus, and you're wondering now, why do I show you something about coronavirus? I know you're probably sick of looking at coronavirus, but it basically explains how the mRNA vaccine works, how the mRNA vaccine basically is delivered into the cell, and we instruct our cells to make copies of the spike proteins. And so that's the important one here. And I'm going to stop that video now. Oh, no, it's gone. Oops. There you go. Okay, I'm not sure if you missed it. But the mRNA vaccine is actually delivered in a nanoparticle. So everybody here got a good load of nanoparticles recently. And that's very important. So there's, and mRNA is just one example, but there are a lot of examples of drug based on DNA, like siRNA, oligonucleotide, that are developed at the moment. They are much better than traditional cancer drugs because they're just so much more specific. They're so much more effective because these DNA-based drugs, we can teach them to really recognize cancer and leave the healthy stuff alone. But the important thing is they don't go into the cell. You would not be able to deliver them without nanoparticles. So the issue is that DNA is negatively charged, and your cell membrane is negatively charged. So if they go together, they get repelled. So your DNA doesn't go inside. But what we're doing is we mix that with something that's positively charged, and together we get a particle. And these particles go on nicely inside the cell and get delivered. And so this is what these lipid particles look like from the Pfizer and Moderna vaccine. So again, they're these molecules you saw before with a negative charge and a positive charge. So we have basically, we use something with a positive charge first. We put it together with our DNA or the mRNA, and then we make a little bit of magic, and you get a particle. That's what they look like. So that is lipid particles, and if we have any chemists here that the molecules they actually used for the Pfizer vaccine and the Moderna vaccine. So question is, this is all fantastic, but where to next? Can I relax now and not do anything and go in retirement? But no, there's still a lot to do. And there's still a lot of hurdles in nanomedicine. So first of all, we really need to better understand these nanoparticles. So far, people were very lucky, but there are a lot of failures as well, and it's because we don't understand the physics of nanoparticles sometimes. We also need to understand what actually happens to these nanoparticles afterwards. You know, we just heard about we all eat credit cards. So when you get treated for cancer or if you get a vaccine, what actually happens to these nanoparticles afterwards? So we need to understand it a little bit. We need to start focusing on other diseases. Actually, cancer is a relative low-hanging fruit, but we have now more and more nanoparticles in clinical trials for other cancers, like other diseases like diabetes, for example. So when we sort of look at the clinical trials that are ongoing, 35% are now other diseases. But we need to also look at better ways of delivering new drugs. So these nanoparticles I showed you for the mRNA vaccine, for these lipid particles, they work great if you target the immune system. They wouldn't work very well for cancer. So we need to look at better ways, and that's sort of my area of research. I really try to deliver siRNA in a better way to treat cancer. But of course, the big future is personalized medicine. So what I showed you during the talk, where you saw a lot of accumulation of a nanoparticle in one patient, there's always a patient that does not respond. And the reason is every person has a very different cancer, and it needs to be addressed quite differently. So there's now a real push before we start the treatment to really understand the genetics of the cancer and design the nanoparticles and also the medicine according to that. And of course, just to make you aware, it's a very long way from the first idea to the market. So these traditional, like Abraxane, Doxil took 10, 15 years. Actually getting a vaccine, getting billions of people vaccinated in a very short period of time was an amazing achievement. It was in 2 years, or less than 2 years, we got that done. But just to show you how complicated this field is, and it requires so many different people working together. And so it's now great that the UNSW actually just established an RNI Institute, where really many people from different fields come together to really make an impact in this field. So we do have people in medical research, we reached out to pharmaceutical industry and so on. So the future of nanomedicine looks bright. It's a challenging field, as I showed you. It's a long journey from injection to the tumor or the diseased site. But when we sort of look at the number of approved formulations, it's slowly creeping up, and we will probably see an exponential growth once we really start understanding nanoparticles. Okay, and with that, I would like to thank you for your attention, and I'd like to thank these 4 institutions for putting this great evening on. I learned a lot, so thank you very much.
Hello, everyone. I'm Ian Woolf. I am the host of Diffusion Science Radio, which is a podcast you might like to listen to about science and technology. You can hear interviews of everybody up here, although the one from Ben is a few years ago. And so tonight, this part of the show, this part of the event is about questions from you that you might have been thinking about during or after the talks. So let's have a look. I was going to ask, let's have a look. Johannes, so I'll just ask a few questions myself, and then I'll throw it to the audience, and we'll get a microphone out to you so you can ask your questions. Johannes, you mentioned sensory science, but you didn't say what it is. So what is it?
Oh, sensory science, you just stop me if I'm talking too much, because that's what I have been doing for nearly 20 years. And this became extremely exciting in 2000 when the human genome had been sequenced. So sensory science is all science related to our senses. And in my particular case, I've been looking at taste, gustation, where taste receptors had been sequenced and identified. This is similar, but not exactly the same, to olfaction, which is the sense of smell. And if you're working on food, needless to say, both taste and smell are of the essence and are really the key drivers for consumers. And again, with the identification of the human genome, there was a gold rush back in 2000 or 2001 in that everybody believed, or not only believed, that the pharmaceutical industry will make big strides in moving forward, identifying reasons and cures for diseases, but also the food industry actually had reasons to believe that we will be able, and we have been able, to identify many of the mechanisms underlying taste and olfaction. And then, of course, you can link that back into what has been done for many years before the genome, which is empirical sensory science, where you have panels, and I don't know if any of you is familiar with what the food industry is doing, be it coffee, where 20, 50 people sit in a room and drink and sip and slurp coffee, to also maybe wine. Australian wine is very good, and I know there is actually a lot of wine tasting going on in this country. And you're developing a very clear language. You're not only talking about sweet, sour, bitter, salty, and umami. You go into astringent. You go into all kinds of sub-modalities in order to characterize your perception. The French are very good in that, and you will also see that actually different cultures and different languages are therefore differently good in doing sensory science. So again, there is a lot of French vocabulary for taste, but overall, sensory science is doing exactly that, has been doing that for many years empirically until the molecular level came in with the genome, and now we can do this in a way more refined way.
Thank you. Thank you. And I was thinking, Martina, can we go smaller than nano, or is that impractical?
It's probably impractical, yes. There comes a point where it doesn't make sense anymore. You're limited by size of a molecule, and you're usually at 1 nanometer already. But having said that, I think we haven't fully explored sort of the nanoscale yet. Most nanoparticles are around 50, 100 nanometers. And I actually want to go smaller than that and explore that sort of the next few years to really explore what happens when we make nanoparticles that are maybe 10 nanometers, and see if we can change the pharmacokinetics by doing so. Yeah, but no, we're not going to have pico particles or anything. Yes.
Wonderful. Let's have a look. Chris, could we round the corners to improve your template so that they can't even use that to hurt anybody?
I think, are they not rounded? Are they not?
They are rounded.
Yeah, they are rounded. Yeah, so
thought of it.
you know, but yeah, I mean, obviously no tool is perfect, and if people are angry enough, they'll find a way to, cut you with paper cuts or something. Who knows? But certainly safety is no joke though, really, because the compasses are like little weapons. I mean, I've stabbed myself many times, and I'm sure you have too. In fact, in some of my videos, you'll see me wearing Band-Aids, my hairy hands with wearing Band-Aids, because I've actually stabbed myself. The other interesting thing about the safety issue is that if I probably wouldn't give a 6-year-old a compass, would you? I probably wouldn't, right? But with a template or a ruler, let's say, it's got a chance, right? It's got a chance. Obviously, kids are still working out their fine motor skills, all that sort of stuff, but at least it's got a chance. So yeah.
Fantastic. And what did I have for Ben? Ben, the photonic routers, how much energy could we really save over the current routers?
Oh, that's a nuanced question. Let's see, how do I answer that? I mean, I made the point that routers consume more energy than the airline industry, and that is true. And about 10 years ago, the energy consumption in telecom was increasing rapidly. At some point, I saw a presentation from the equivalent of the chief scientist of Japan, who had foreshadowed that if nothing was going to change, Japan's energy budget was going to be dominated by routers within 10 years. And then Japan turned off its nuclear power stations. And it didn't happen. Unfortunately, that's because we innovated. And we brought photonics into the router. And so we've already addressed some of that issue. I guess the question, too late on Friday after a glass of wine to give you a quantitative answer, but photonics is driving bandwidth and reducing energy consumption. It has already massively reduced. There's also a long way to go, and there are some fundamental challenges. So one way of answering to kind of distract from the actual question, but to say that what we don't know how to do is make a photonic buffer. So routers are switches and our buffers. Switching photonics is easy, but buffers are hard because slowing light down, it turns out to be a very difficult problem for fundamental reasons, and that's ongoing research. In fact, I was teaching a fourth year class today on exactly this topic. Typically, it is done at cryogenic temperatures. So there's still some great science. So if we can slow light down, if we can stop light, we can make a photonic buffer, and then we open up another 2 orders of magnitude bandwidth, but that's probably 10 years away.
All right, now it's over to the audience. So if you want to put your hand up, there should be a roving microphone. Fred's got it at the back, and he'll bring it over to you. And you can, and if you just ask your question, and I'll pass the microphone along.
All right, I got a question for Martina. I was just reading on the internet there that without antibiotics, our life expectancy would be about 50, which is probably not great for a bunch of us in the room here, and I've probably got a few years left to go myself. With nano medicine, how much is that going to extend our lifetime once it becomes mature and ubiquitous?
Oh, that's it's very hard to put a number on these things. I don't know, to be honest. I never really thought of it expanding overall life expectancy, but I thought of it as a tool if when somebody's sick, to treating them better. So yes, unless we. I can't really say. No, it's. I can't really say. But one thing I can say is that nanoparticles invade different areas now. When you say antibiotics, people use nanoparticles now, for example, to inhibit infections. And so the nanoparticles now invade all these different areas. And don't forget, nanoparticles can also are fantastic diagnostic tools. So a lot of improvement in increased cancer survival we've seen over the last 10, 20 years. It's not because of better treatment, but very often of better diagnostic beforehand to pick up the cancer earlier. It's also very often thanks to nanoparticles that they can do that much better. Yeah, but I can't put a number on living longer. Depends how good your food is.
Well, that was my second question. Let's assume it's 20 years. Johannes, can we eat if everyone's life expectancy is increased by 20 years?
Well, it actually might be the other way around. If you eat well and if you eat right, you might extend your life expectancy or health expectancy by 20 years. And that's not even a joke. So there is good reason to believe that right food makes you live longer. There's a lot of research into health span extension and longevity. And all of these molecules turn out to be in our food. So, yes.
Red wine.
Yeah, or resveratrol. There you go.
Okay, so question.
Oh, okay. Sorry, Martina, I had to ask you this question again.
Okay.
Another one. I was part of a research group at St. George Hospital where they did a similar sort of research to yourself. Instead of using nanoparticles, they used radiation called targeted alpha therapy. The alpha particles killed the cancer cells, individual one, because it's got a very short range. But they were very surprised that it actually killed the tumours as well. And we couldn't work out why it was doing that. And what we discovered was it's actually destroying the vessels, the blood vessels going to the tumour. So my question is, could nanoparticles actually disrupt the blood vessels feeding the tumour?
Yeah, well, there's some research not using nanoparticles but microparticles where you put these big particles into the blood vessel leading up to the tumor, and you basically starve the tumor to death. So it's more mechanical approach, more or less, to do that. But nanoparticles themselves, they do something funny to tumors as well. What we found in our research is that nanoparticles themselves, they can sometimes inhibit the movement of tumor cells, and which is very important when you think of metastatic cancer. Metastatic cancer is all about a cancer cell moving somewhere else, and we found just a nanoparticle, no drug, inhibits that. So I think there's so much we don't know about nanoparticles yet and what they can do at the same time. But going back to your question, I think you're probably referring more to almost a mechanical approach of really blocking the blood access to the tumor. And in some ways, I could think about having nanoparticles that sort of accumulate over time and really form a cap to these blood vessels. So there's probably a possibility to do that as well, because a tumor is it has very leaky vasculature, and so if we just use that as a way of getting all these nanoparticles in there until it sort of fills up the space, there might be an option. I just don't know how many nanoparticles we actually need.
Yeah, that was happening. It caused the leakage of all these blood vessels by the radiation.
Yeah. Good. Does it sort of?
Yeah, sure.
And just down the front here.
I was trying to think of a question that could kind of synthesize all of the talks. And,
Good luck.
So my question is like this. I'm thinking of a template to really get to the next level of understanding how we can look at disease in cells or even cell function. I came across an interesting paper which was published fairly recently, which looked at thermal gradients in cells and the change in temperature across cells. And these very clever researchers got nanodiamonds and put them within the structures in the cell and found, in the mitochondria you'd expect it's a little bit hotter, but we didn't expect to find it was nearly 2 degrees hotter, not just fractions of a degree. So I'm thinking of your type of worlds that you're living in, and then I'm thinking of Ben's world, where he can put light into just about anywhere that he thinks about putting it. That could we have a new way of imagining the cell as taking things which are really at the moment like balls of string and unpacking them a little bit more elegantly using some of the tools that Ben has got and the toolkit that you've got to really get to functional analysis at the level of the cell instead of taking it out, putting it in a computer and hoping it's doing what is happening in the cell. So it's a very open-ended speculative question, but I was amazed by this paper really showing so elegantly that there are these thermal differentials in cells that nobody really knew about, and they're big.
Okay, so who wants to answer first?
I think that's your domain more than my domain, but I think they're starting to think that through. I mean, there are, what do we call that? Don't we have a name for that type of? Optogenetics, that's right. So that's a reasonably mature field of using light sources from outside the body to activate at the nanoparticle level and at the cellular level. Yeah. So yeah, indeed. Yeah, they're probably you're more qualified than I am.
No, that's my previous research field. But out of Germany, a group has discovered a molecule very similar to our rhodopsin in our eyes called channel rhodopsin, which is basically a molecule that would let ions go through the membrane upon illumination with a photon, and that's again similar to the molecule I've been studying during my PhD, bacterial rhodopsin, which pumps proton, which makes a reference to your point about friction in the membrane, which heats up the mitochondria, and that's exactly what's happening there. So optogenetics, I would predict here, in front of everybody, will give a Nobel Prize at least to one of those German guys within the next 5 years. So don't quote me on that. So, but it's a super exciting field, and yes, I think at the end of the day, if I understand your question correctly, there might even be a way to build something like cellular computers that are controlled and guided by or switched on and off by light. I mean, yes, exactly. I can
even smaller machines.
I can see that very clearly at the horizon. Yes.
All right. So next question. Oh, over here.
Yeah. Hello. So my question is like for Johannes regarding like growing like meat in the lab. So how much can kind of benefit to our footprint if we consider the cost of like the clean room, the sterilization of everything, and so on? So,
Very good question, and certainly an ongoing discussion. There was a big controversial, a science paper. It was published not in a scientific journal, but in the Counter, a publication that I've never heard of before, but coming here with a lot of Australian input into this field. And the quick and dirty answer would be, this remains to be seen, like energy costs, real greenhouse gas emissions. The belief, though, is that if we get this right and if we get this done with the cell-based meat, we have way more control over the system than what we would have on a cow that's running up and down the meadow, in that the cow burps and has other releases that just go straight into the air, contributing to greenhouse gas, right? If all of this happens inside a controlled environment, we might, if we put our head to it correctly and if we get this right, we might have a chance to manage this in a better way.
okay, thank you. I have a question for Ben as well, if it's okay.
Oh,
So, when we have like waveguides like that, they are very long, that there is like problems that phonon excitations, and you may need to put extra energies and so on. So in a futuristic kind of like view, like could we picture, I don't know, like information transfer without like waveguides, so just by laser or anything like this?
Say it again in one sentence, and I'm not getting the essence of the question.
Yeah, so like from a futuristic point of view, okay?
Yeah.
So if we want like to further increase like kind of efficiency, or like could we try to devise a way to like transfer information without the physical support like of the wave?
Well, that's
like laser
sending
transfer.
light through space.
Yeah, for instance, or satellite, for instance, to ground.
We do that routinely.
Okay.
So, indeed, I mean, the simplest example of that is me standing on one side of a park with a torch and moving my hand up and down in front of it, and I'm creating a Morse code kind of signal. Someone on the other side of the room sees the light going on and off. So we do that, satellite communications, we do optical. Elon Musk is building a worldwide network based on low Earth orbit satellites. So yes, free space communications, that's a concept. It's mature. I mean, an example that makes it really clear, I was in New York at 9/11 when they knocked out downtown Manhattan. They knocked out the entire fibre optic network, and within 24 hours they had rolled out free space communications. And essentially it's like a telescope, a system that sends a laser from New York to New Jersey at the speed of light.
Thank you. Yep. Yeah, I also wanted to mention about Starlink. That was a great example. And I just noticed that there is a lot of research at Macquarie going on about infrared lasers. And I'm just curious, when it comes to photonics on the chips, is there any preference in terms of wavelength? Would you like to have like blue light or probably like a red light? And what's the benefits of each?
Yeah, good question. We tend to fixate on the near infrared. As a research community, 1.5 microns for one very simple reason, and that is optical fibre networks are designed to operate at 1.5 microns for a very simple reason, and that's because the erbium-doped fibre amplifier operates at 1.5 microns. So every amplifier in every optical network, every optical communication link on the planet relies on erbium-doped fibre to amplify light, and they operate at 1.5 microns. So for convenience, we always focus on 1.5 microns. But indeed, the infrared, the mid-infrared in particular, 2 microns to 10 microns is very interesting. Infrared, thermal, molecular fingerprint, interesting for sensors. Defence is very interested in the infrared. And then as you go to visible, there are numerous applications. So, yeah, good question. Silicon, as a great material for microelectronics and photonics, turns out to be very good at 1.5 micron. But the band gap of silicon is in the visible, and it's opaque in the visible. It's like brick in the visible. It's good at the near infrared, it's pretty good at the mid infrared, but it's completely opaque at the blue. Silicon nitride, another interesting material for photonics, is good in the visible, it turns out. Yeah, good question.
Thank you. You can bring the microphone. Oh, sorry, there's one at the back. We'll be you next.
This is the question might be a bit abstract at the moment because it's like a science fiction, but having great frontiers here, I wish to put forward this idea, especially at this COVID situation. I'm thinking about people were talking about template, microelectronics, all that. But now, can we make lipid nanoparticles as a template which has the capacity to incorporate artificial intelligence, like machine learning capacity, that can actually monitor the variance, and then it can evolve itself within your body.
Is anyone
sorry for this, but would like to address that? I think we have to come up with an answer together here.
A couple of decades, couple of billion.
I have an interesting perspective.
Okay.
Here we go.
It doesn't answer the question, but there is some really interesting research at Sydney and at UNSW in nanorobotics. So this is an emerging field. And we've looked, and Susan Ponders here was part of this discussion when she was, when you were director of Einstein Nano. We looked very seriously at the idea of constructing cellular scale hybrid CMOS lipid-based robots. Okay, so this is the concept from science fiction of constructing an autonomous, powered, mobile, functional particle of the order of the scale of the cell. Now, it's conceivable. Now, I made the point, how big is the size of the smallest transistor? I did say that in my presentation.
10 nanometers.
10 nanometers. So you can do the math. You can actually say, okay, if I have a cellular scale robot that has the ability at a cellular level. Now, remember, the cell's still much bigger than the DNA. So I'm miles away, but I'm a step towards it. I've got enough real estate. We've done the calculation. I've got enough real estate that I can load into that 10 to the 4 logic gates. It's not many. Unless I'm doing quantum computing, and don't even get me started on doing quantum computing, because quantum computing for the next 20 years is going to involve a building the size of the Faculty of Medicine and Health. Okay, so it's not going to be compatible. But that gives you an idea. So the notion of equipping a cellular scale functional component with intelligence, probably between 10 to the 4 and 10 to the 5 logic components is possible, which is not going to give you AI, but it might give you the basic analog functions to do sensing, communicate, navigate, process basic information. Then the last comment I would say is that at the level of the DNA, we've got researchers at Sydney and at UNSW who are exploring the notion of self-assembled DNA origami. So it turns out, and I'm less an expert than my colleagues here in this area, it turns out that DNA have some exquisite properties, including the ability to self-assemble and to self-assemble into functional components that are building blocks of DNA scale robots. Okay, so does that get a little bit close to what you're imagining. And I'll pass to my colleagues here who might want to build on that or take it in a new direction.
No, I think you answered it really well. No, I'm not sure if I have anything to add there, but I think if we can fill these liposomes, but also use the liposome itself with some clever chemistry together, I think you can probably build something. But as I said, well, the space is still very small. Yeah, but we can, you're familiar with the liposome field, Sachi, so you know that we can have chemicals that respond to light, that respond to temperature, and change maybe their shape as well. Yeah. Yeah. So we can maybe have a level of control on top of it, but yeah, it's a nice idea. And then you have to feed the information back as well.
I have a question. If we're in the business of really out there, so I saw the latest James Bond movie. Now, aside from the fact that I'm pretty unhappy that the ending, I'm still confused.
No, it's written he will come back.
Well, that's right. So whatever was that, there was quite an incredible scene in the movie that talked about the idea of a weapon that is based on the ability to program a virus specific to the DNA of individuals. Pretty scary. So literally imagine the room we're in. Someone walks into this room and scans in real time every person in the room, and in real time has a database of their DNA. Now, it sounds extraordinary. Probably isn't that extraordinary. I mean, we look for RNA DNA in our sewage, and then can program a virus. This is the Hollywood movie. This is the James Bond. Is that conceivably possible in our lifetime? Is that just totally out there? Do you get what you've seen the James Bond movie?
Yes. I think it's...
I haven't, but I get the idea. Very evil thought. Well, I'm not. The idea is really somebody comes into this room here and has maybe a little scanner, and here we go, Johannes. That's it.
Well, yeah, so putting that aside, but can you program the notion of programming a virus that is tailored to a specific DNA, an individual?
I can say something.
Yeah.
I think if we are, and we're doing this with nutrition, but it is sort of copied or just the evolution of personalized, and Martina mentioned this, personalized medicine led to personalized nutrition. So if we do personalized medicine, and we are doing it, and if we can heal people in a personalized way, we will also be able to kill them in a personalized way. Yeah, absolutely, absolutely. No,
we already got one of those today. Here's a weapon of mass.
So did you get Chris? Did you get Chris's comment on that?